Welcome to the fourth episode in a series where we're taking a hands-on look at how electric motors work. If you want a better understanding of how electric motors work, or are considering to try to build your own, then stick around, and maybe check out some of my other videos too. A quick thanks to all those who have subscribed and stuck around. At times the video releases might be a little bit patchy, but I usually will get there in the end. For those waiting for more mini-lathe modification or machining stuff, I will definitely be doing more of that in the future, but honestly it's not really a hard genre channel. I just cover things that grab my attention, and I guess my hope is that they will interest you too. In the last video, we took a look at how magnets and electromagnets interact and got a better understanding of the forces involved. In this video, we will take a look at those same magnets and see if we can make a couple of different experimental motors with them. I've designed and 3D printed out a few copies of this simple rotating test jig. For the first experiment, I've installed two magnets into the outer case, and this part does not move, or is stationary. It's called the stator. And the other two magnets are installed in the center rotating part, and that's called the rotor. I have the polarity of the magnets in each part, such that the north and south poles are all facing each other. And as you might expect, the rotor has a natural tendency to want to align with the opposing poles in the stator, resulting in all the north-south poles facing each other. Forcefully trying to move away from this alignment, we can feel a strong pulling force. This weakens somewhat at about 90 degrees. Keep rotating so that the like poles start to align, and we can now feel a pretty strong pushing force. And if I'm really careful, I can actually get it to balance here, where you would expect the opposing forces to be the strongest. With a nudge, it will swing back in either direction, pretty violently actually, back to where the pulling forces are the strongest. You can actually see it bounce around a little bit. This is due to the momentum of the rotor causing some overshoot as it tries to settle where the attraction is the strongest. Really the only thing motor-like we are seeing with this test is the momentary but powerful partial rotation. But it does provide some useful clues, which helps us understand what might be needed to get full and continuous rotation. Now I'm not exactly sure which pole is which here, but let's say the black dot on the rotor here indicates south pole, and the magnet in the stator here where the attraction occurs, we'll say that's the north pole. As we approach from the top, we feel a pull of the magnets, and if we release there's a slight overshoot and a settled wobble, just as we saw before. But now imagine that just as it overshoots, the magnetic polarity of either the rotor or the stator could magically be changed. Let me simulate that with my magical hands. Now instead of a pulling force, we get a pushing force, allowing the rotation to continue in an anti-clockwise direction. And of course, changing this continuously gives us continual rotation. Alternatively, if we approach from the bottom and make the change as the rotor overshoots above, we get a clockwise rotation. Simply put, we could get this motor to rotate properly if we can switch the pulling force to a pushing force just as the rotor overshoots the settling position. And on which side these pulling or pushing forces are maintained decides the rotational direction. So how can we achieve this polarity switch? Well, you can imagine some type of mechanical arrangement where the spinning shaft automatically causes either the rotor or stator magnets to flip around. That would be pretty cool. You could have a motor and you don't need any power. But sadly, it's not that simple. In reality, to make magnets flip like that, you're going to need some energy. And conservation of energy means there's no free lunch. Any force on the rotor is going to cause a force that will need to be overcome to spin those magnets around. The unloaded friction of the motor mechanism itself presents a force to overcome. And then when you start applying an application load, this force also then needs to be overcome. Now it's pretty easy to get obsessed with the magical powers of permanent magnets. And a number of interesting people have designed interesting mechanisms to try to extract free energy from them. Unsurprisingly, however, we still don't have any free energy motors, right? Personally, I like to think of permanent magnets as behaving a little bit like gravity. Gravity allows you to create potential energy by lifting things up to a height, but you need to use energy to make that potential energy, right? It's not free. Pushing two like-pole permanent magnets together also takes some energy, but it's also creating potential energy which you can release later. Creating potential energy is not actually making new energy. It is just converting energy into a stored form, usually with some sort of overhead or loss in the process as well. So even though permanent magnets continuously emit a magnetic field, they don't actually create any new energy. Now hopefully I didn't destroy anyone's dreams of a free energy machine with that little explanation, but that's just the way it is. Okay, time to give up on the permanent magnet only motor and switch out two of the permanent magnets with electromagnets. Using electromagnets, we can electrically control the polarity and strength of the magnetic field, but naturally we're going to need to power them as well. Really the tricky bit is going to be synchronizing the switching, flipping the direction of the electrical current just at the right time. The most immediately obvious solution that I could think of was to mount two electromagnets here in the stator and then have some type of mechanical switch actuation locked to the position of the rotor. Imagine a little arm on the shaft of the rotor that toggles some tricky switch mechanism. Now, I'm not going to think it out in detail, but obviously it could be possible, even though likely a pretty awful design. In reality, a much better solution to this switching problem was already invented nearly 200 years ago. That solution was the brushed electric motor, a solution that is still widely used today, and I'm pretty sure you're aware of. This design has the electromagnet as a part of the spinning rotor, with the permanent magnets installed in the stator. Current is supplied to the electromagnets by using brushes that contact with the shaft, with some type of spring force to keep the brush in contact with the shaft, of course. Now, I'm drawing this shaft ridiculously large here, only for the purpose of easier visualization. But on the shaft here, we have these electrical contacts, and these contacts on the shaft are known as commutators. And they're arranged so that the current flows through the electromagnet in a given direction, dependent upon the rotor's position. This keeps the pushing and pulling forces changing just at the right time to keep the motor rotating. Changing the motor's direction is also easy. Simply switching the direction of the current supplied to the brushes changes the polarity of the electromagnetic field. This in turn swaps the location of the pushing and pulling forces inside the motor, naturally giving a reverse direction. On the test jig here, I've swapped out the rotor's permanent magnets with some electromagnets, and I've wired these to a copper tape commutator which I've added to the shaft here. There are also a couple of springs here I've added that I'm using for brushes. You can see there are some slits here in the copper tape. This is positioned so the polarity will switch just as the magnets face each other. Now, as I'm using steel cored electromagnets in the rotor, this has a natural tendency to want to align with the stator's permanent magnets, as you can see here. If you've ever manually spun an electric motor, you'll probably have noticed a similar tendency where it sort of notches around a bit. Alright, let's apply some power and see if we can get this to spin. You can see it's running pretty lumpy, somewhat due to the geometry of the motor that I've designed and the fact that I've not secured these magnets properly. But the steel cord electromagnets are also likely pulling much harder than they are pushing, and that's causing probably a little bit more lumpiness in the running as well. If you want to know more about that, then check out the last episode to provide some useful insights into this phenomenon. Now, the brushes are not keeping great contact either. You can see plenty of sparks here burning away the armature and brushes. And as you might expect, increasing and decreasing the current supply changes the speed. But why exactly is that? What's controlling the speed this motor rotates at? Well, let's look at the forces involved here and put aside the spinning aspect for a minute. Ultimately, the motive force is the interaction between the permanent magnets and the electromagnets, and if no other forces were at play, we would see a continuous acceleration resulting in our rotor just simply getting faster and faster all of the time. But opposing forces do exist, such as friction and air resistance, and actually these are going to increase as the rotational speed increases too. And then of course we have the application load, which can also vary over time or at a given speed or something else. The motor can only keep accelerating for as long as the force the motor is generating, the motive force, is greater than that of the total opposing forces. I guess ultimately the point I'm trying to make is that this is a balancing act, and it's the point of balance that ultimately determines the rotational speed the motor achieves. Even though we are seeing polarity switching of the electromagnet that increases in frequency with speed, this is more of an effect and less so the cause of the speed. If we reach the force balance point but want more speed, the only way to achieve that is to push more energy into the electromagnets. I think this has good parallels with gasoline motors too, with ignition being the point the piston changes direction and that being locked to the rotational position of the engine, typically using a distributor. To increase the speed, you need to add power to the system by adding more fuel-air mixture, resulting in a more powerful explosion, pushing the piston harder. Just as with electric motors, you increase the energy level necessary to overcome the opposing forces, ultimately reaching a balancing point that results in the final speed of the motor. Okay, enough of that. Next, let's turn this test jig into a brushless motor and see how that works in comparison to a brush motor. One of the key design points of a brushless motor is obviously the lack of brushes. Naturally, getting rid of the brushes gets rid of a chunk of frictional load, as well as mechanically wearing and consumable parts. Other than that, we will still need to achieve pretty much the same thing we saw with the brushed motor, and that being the synchronized switching of the push and pull forces with relation to the rotor's position. But without the brushes, we're going to lose the ability to power those magnets inside the rotor, and we also lose our method to synchronize that switching. And anything we do to solve that can't really add any frictional load to the rotor, as that would be simply robbing Peter to pay Paul. So the first thing we can do is place the electromagnets into the stator, which is going to make it pretty easy to wire to them. But we also need a way to contactlessly sense the rotor position. In this case, I'm going to use a mask disc on the rotor and an optical sensor. So here you go. I've got a new test jig and it's got the electromagnets in the stator and the optical sensor installed. And just a little interjection here, real world motors are more likely to use Hall sensors and not the optical sensors that I'm using here. And a lot of hobby motors actually use senseless arrangements that had the electromagnets in the stator pull double duty, both driving the motor and sensing the position. Sensorless motors do, however, require the motor to have some motion to detect the position, so that can be problematic and cause some undesirable side effects in some situations. But with less parts and cables, you can understand why they've been pretty popular in the hobby domain. Now let's take a look at the controller design for this simple brushless motor. First, here is the sensor signal coming in, and here is the magnetic coil that we want to drive. The switching arrangement for the coils is going to look something like this. And if you saw the first episode of this series, you will instantly recognize the high and low switching arrangement that I'm drawing here. If we switch on these two switches, which I will mark with an A, we can get the current to flow through the coil, positive here and negative here. Alternatively, if we switch on the other two switches, which I will mark with a B, we can reverse the polarity with positive here and negative now here. Here's roughly what the sensor signal is going to look like. The A switches will be controlled directly by the sensor's signal output, but the B switches will be controlled by an inverted version of the sensor signal. This will ensure that only one set of switches are ever turned on at one time, avoiding any risk of short. And of course, the switching timing will be directly locked to the position of the rotor at all times. So here's the sensor wire. It connects over here to the inverter, a 74HC04. MOSFETs for the switching are paired horizontally. Low side MOSFETs are all located on the right side here, and the high side MOSFETs are on the left side. I'm also using an old salvage DC to DC converter to make a 12 volt rail from the 5 volt rail, and using NPN transistors, I'm converting the high side control signals to 12 volt logic. I'm doing this to address the high side switching problem that typically comes with this type of design. If you want to learn more about that, then check out the first episode in this series. Unfortunately, this conversion method has the side effect of inverting the logic, so I need to provide an active low signal from my controller logic, and that's easy enough to do by providing an inverted version of the control signal. Okay, let's power it up. The power switched by the MOSFET is actually coming directly from a separate lab power supply, so I'm using that to control the amount of current that gets to the motor. I have two LEDs also connected to the switching circuit here. Either LED will light up depending on the direction of the current. Now the camera shutter speed is actually messing this up a little bit at high speed. In real life those LEDs are just constantly on, but anyway, just ignore that. Wow, at this intermediate current level you can really notice the magnetic force lumpiness. This is likely due to the steel cord electromagnetics behavior. And it makes sense given what we saw in the last episode's experiments. Okay, now let's check the slow speed performance. Pretty smooth and stable at low speeds, much better than the brush motor, likely due to the lack of brush friction. So there you go, we have a simple brushless motor. Now I'm sure that most of you have noticed that this brushless motor is pretty much doing exactly the same thing that the brush motor was doing, albeit with a little less friction. Just as with the brush motor, the RPM achieved is ultimately dependent on the forces balancing out, with the switching timing just following along for the ride. However, comparing the designs, it is clear to me that there is one thing you can do with a brushless motor that could not be done so easily with a brushed motor. And that is the ability to dynamically change the relationship between the rotor position sensing and electromagnetic switching. For brush motors, the timing is physically locked into place, pretty much baked in. But for brushless motors, we can add something like a microcontroller between the sensor and the switch, allowing for the option of adaptive timing. Now, if you saw the first episode in the series, where I tore down an ESC, you remember that a microcontroller was being used instead of fixed logic like that I'm using here in this demonstration. Naturally, once you bring a programmable computer into the mix, it's going to open up all sorts of possibilities as to what you can do. Okay, for the last bit of this episode, let's bring in the PWM controller that we made in the last episode and try to connect it up to these motors. For the brush motor, it's pretty straightforward. I'm just going to use the exact same circuit that we used in the last episode when we were driving those magnetic coils. So let's give that a go. You can see the speed can now be controlled by the PWM controller. It's really as simple as that. For the brushless motor, however, simply trying to connect the PWM's MOSFET to the high-load MOSFET switching circuit is likely going to mess some things up a bit. So instead of doing that, I'm going to integrate the logic signal from the PWM controller directly into the high side switches control, which is easy enough to do by adding a couple of AND gates. This means that the low side switches are going to work exactly the same as they did before, but the high side switch will now only activate when the sensor selects it and the PWM pulse is also high. So the high side switch is now going to have a dual role, right? Which saves us from adding more MOSFETs in the design for the PWM switching. So here is the AND gate that I added to combine in the PWM signal. Actually, it's a 74HC00 NAND gate, and I'm using that to get the inverted version of the high side signal that we need. Okay, let's set it up. Looking good. Start to slow it down. Again, we see very stable slow speeds. Really good controllability with the PWM signal. Let's see what happens when we try to max it out. Geez, that thing's really flying. Well, starting to warm up a bit here. So I've got the lab power supply set around about 8 volts. So at 3.4 amps, we're probably burning around about 27 watts. The current and the speed is also dropping off a bit here as the internal resistance is increasing with the heat. Thing's trying to run away. Get back here. Slow it down. Slow it down. And see where it stops. Stops at 25% PWM. It's around about 300 milliamps. I'm going to need to give it a helping hand to get it going again. Wow, up to 60 degrees Celsius at the case. So the electromagnets themselves are likely getting well hot enough to deform the PLA, I'd say at that. I'd definitely want a better cooling design if I was actually making a real motor for practical use. So what about reverse direction for this brushless motor? Well, that can be done in Logic too. All we need to do is invert the sensor state, and that will reverse the direction. To do that, I will add an XOR gate here. This will act as a selectable inverter. When the switch is on, it will invert the sensor signal, and when off, it will simply pass the signal in its original state. So here is the sensor signal, now going to the XOR gate first. The direction switch is also connected here, and the XOR output is going to the original inverter circuit. Starts up normally. Flip the switch and boom, we have reversed the rotation. Let's try that at higher speed. No problem at all. And what about full tilt? Cool stuff. Now I wanted to address the elephant in the room. I'm sure many of you have noticed that the brush motor actually shorts the polarity at the crossover point. And even if you could design a very small gap and a small contact point for the brushes, there will always be a position in the rotation where the motor cannot actually start. For this single phase switching design, trying to start the motor after it is stopped right at that switch point is simply problematic, even for brushless versions of the motor. And my test design here with the steel cored electromagnet only makes this problem worse, given its natural tendency to want to stop right at that switch point. The solution for this is to use 3 phases instead of 1 phase as I'm using in this design. For brushed motors, this means a tricky armature or commutator design, and with no possibility of the brushes ever shorting out. Even so, the motor is always energized at all points of the rotation, meaning that there's no dead zones like we're seeing with this single phase design. It also means you can get a nice rolling handover of the magnetic forces, and that can make the motor run a little bit smoother as well. As far as I can tell, pretty much all modern electric motors, be it brushed or brushless, are using a three-phase design. Sure, you may see brushless motors with many more than 3 coils in the stator and think that, it must be more than 3 phase, but the number of coils usually will be a factor of 3, with the energizing method only being 3-phased. And of course, the 3 power wires running to the motor is a dead giveaway that this is actually a 3-phase motor. And if it is a brushless motor with sensors, you're typically going to find that it has 3 sensors too. So there you finally have it. You should now have a pretty solid idea of how a typical electric motor works. Hopefully that will provide useful knowledge should you be dealing with off-the-shelf products or should you decide to try to build your own stuff. Now if you like the video and you want to see more, then consider subscribing or dropping a comment or liking. Really anything helps. I do hope to see you in the next episode where I'm intending to break out the oscilloscope and take a look at some of the signals in the ESC that I tore down in that first episode and see what we can learn. So see you then. Now if you managed to watch this entire video and are still watching right now, then please do me a favour and leave a comment simply stating, I survived. Yep, that's right, I survived in the comments. Seems appropriate, right? But in all seriousness, this will help me get an idea about how people are actually watching these videos. So thanks so much in advance.